Okay. Hello to those watching this video in the future. I'm David. I'm the coordinator of the Maths Learning Centre here at the Uni of Adelaide, and this is the revision seminar for Maths for Data Science. It's semester 2, 2022. And welcome. And I'm going to be talking about series and Taylor series because that's the request I've had. Okay. I'm going to start out by actually looking at an existing problem to see what it means, and then we can pull apart the meaning and talk about what each of them means as we go along. So this is taken from the course notes, this example here. If we use the Maclaurin polynomial and Pnx for e to the power of x, find the smallest value of n which gives e, which is e to the power of 1, to within accuracy of 0.12345. Okay, so this is the problem I've helpfully been given, and we're going to talk about all the things that this problem is about, and then we'll actually do the problem. Okay. So problem solving requires you to understand what the problem's asking you to do, and so you need to know what all of the words mean and all the symbols mean in order to make sense of what it's talking about. And the first word that I've come to is the Maclaurin polynomial. And the way this grammar of this sentence says, if we use the Maclaurin polynomial Pnx, this Pnx is the symbol they're using today for the Maclaurin polynomial, and you'll see that the Maclaurin polynomial is for this function e to the power of x. So a Maclaurin polynomial must be a thing that belongs to a function, and so we need to know what that means. So a Maclaurin polynomial is a special kind of Taylor polynomial, and a Taylor polynomial is an attempt to write a function as a polynomial. So the idea is this. Given a function f of x, the Taylor polynomial for f of x at a, can I just call it, I'm just going to call it C, it might not be, just one moment. No, at a degree n. So just before I even say what it is, you can see there's three prepositions here. It's for f of x at a particular spot of degree n. There's three descriptive things about the Taylor polynomial, and it doesn't really matter what order you say them in. So you can say a Taylor polynomial of degree n for f of x at a, or a Taylor polynomial at a for f of x of degree n. Doesn't really matter what order they're in, as long as they say the right preposition with the right thing, it will work. And so the way it works is this: you start out by doing f of a as a constant. So you sub this number into the function, and you, so that's what you'd start with first. And then you do another thing where you do the derivative of the function, and you sub in and you multiply that by x minus a, and then you do the second derivative of the function at a and divide by 2 x minus a, and then you do the third derivative of the function at a, and you divide by, now each time the denominator gets multiplied by one more number. So the denominator here is 1, the denominator here is 1 times 2, the denominator here is 1 times 2. Sorry, this mosquito keeps buzzing in my ear. 1 times 2 times 3, so this one will be 3 factorial cubed. This will be a squared here, sorry. And then the next one will be, and you'll just keep going until you stop. So this brackets 4 is short for the fourth derivative. So here I've done dash, dash, dash. I'm going to put in brackets the number 4, so I could have put here in brackets the number 3, and that would have meant the same thing. So just keep doing that until you get to the end. So until you see, look at this, this is an x, this has got an x to the power of 1, this one will have an x squared when I expand it out, this one will have an x cubed, this one will have an x to the power of 4. So you'll keep going until you get to a last one. And then you'll stop. So it is possible to have a Taylor polynomial that stops earlier than I've done here. You can stop here, or you can stop here, you can stop here, you can stop here. So just to be absolutely clear, I'm just going to stop and do one more thing. It's traditionally called Pnx. But there's nothing stopping you calling it anything you want, but it's traditionally called P for polynomial, N for the degree, and X. So unfortunately, the notation that you write here doesn't indicate what the value of A is. And so there will be a different one for every A, but you don't normally tell people what that is in the notation. So just to be clear, for f of x at A of degree 1 is f of A P1x, is f of A plus f dashed of A x minus A, and of degree 2 is P2x f of A plus f dashed of A x minus A plus f double dashed of A on 2 x minus A squared, and degree 3, and so on. Each one has one more piece. This is the degree 1, it stops with x minus A in the first derivative. This is degree 2, it stops at x minus A squared and it has the second derivative, and so on. And so on. If I want degree 4, I'll go to the next term. If I want degree 5, I'll go to the next one after that, and so on. I can stop anywhere I want. How do you feel about that? Cool. So I've talked about Taylor polynomials, but the actual terminology that's in this question, it says Maclaurin polynomial. And that's because Maclaurin invented this thing before Taylor did. And he only did it when the center A is 0. I call this the center, that thing there. Other people call it other things. And I should also say that the word at could have been about or around, possibly. That would have been as well. Any word that says that this is like a location will do the trick. Okay. So a Maclaurin polynomial is a Taylor polynomial centre 0, basically. And so that would mean that, you know, you'd get Pnx would be f of 0 plus f dashed of 0 on nothing, f dashed of 0 times x minus 0, which is just x, plus f double dashed of 0 on 2 times x minus 0 squared, so just x squared, and so on. So a Maclaurin polynomial is different from a Taylor polynomial, and it's a special Taylor polynomial, and it looks different because you don't have the x minus a bit because the a is 0. Yeah, so that's what makes it a Maclaurin polynomial. So if you wanted to find a particular Maclaurin or Taylor polynomial, you would have to find the derivative of your function, and you would have to find the sub in the centre, and then you would have to write down the polynomial. And the very important thing is you do not expand out this x minus a cubed. You don't do algebra to expand that out into bigger things. You just leave it exactly as it is. Okay. So in this example, I could, if I wanted to, actually calculate the Maclaurin polynomial for e to the power of x, but I'm pretty sure the people in this course will expect you to remember the Maclaurin polynomial for e to the power of x. It's one of the classic series that you're supposed to remember. So you could do this, but you don't have to, but I'm going to say this. So you could do this. So you could say f of x is equal to e to the power of x, and f dashed of x is also e to the power of x, and f double dashed of x is also e to the power of x, and f triple dashed of x is also e to the power of x, and so on. And f of 0 is e to the power of 0, which is 1, and f dashed of 0 is also 1, and f double dashed of 0 is also 1, and so on forever. And so the polynomial is we start with f of 0, which is 1, plus f dashed of 0, which is also 1, times x, plus f double dashed of 0, which is also 1, but I have to divide by 2 times x, plus f triple dashed of 0, which is also 1, divided by 3 factorial, which is 6 times x squared, plus, and it will end somewhere here, like that. That is the Maclaurin polynomial for e to the power of x of degree n. And you're supposed to be able to remember that, to say that each x is multiplied by 1 over the power factorial. Okay. But that is the process of how it works. You have to figure out what each of these is. You have to figure out what this is. If you're very lucky, you can make a formula for what this one is, for the nth term. Right, so that's that. So when it says the Maclaurin polynomial for Pn of for e to the power of x, all of this is sort of in your mind, but the actual answer for what that Maclaurin polynomial is this. But they didn't actually ask us to find the Maclaurin polynomial for that, so we don't actually need to do that bit. What they asked us to do was to find the smallest value of n, which gives e to within the accuracy of 0.00005. So, 5 zeros. Which means that we are trying to figure out how different this is from this. Because when they talk about accuracy, they mean how far apart the polynomial's answer is from the actual answer. Because e to the power of x is not a polynomial. It does not do the things that polynomial is supposed to do, but it is approximately equal to this polynomial. And we want to know how far apart they are. So what I'm imagining this is the picture I'm imagining. Here's e to the power of x, it looks like that. And e to the power of 1, It's about 2.71818, right? That's what e to the power of 1 is. So what I'm doing is I'm making a Maclaurin polynomial with centre 0. So when you make a Taylor polynomial, you make a polynomial that has the same derivative as this e to the power of x does at this spot, and the same second derivative at this spot, and the same third derivative at this spot. So what will actually happen, in fact, I'm going to switch over to Desmos. Not that you can use Desmos in the exam, of course. All right, this is Desmos. So I'm going to say f of x is equal to e to the power of x. That's what e to the power of x looks like. And I'm going to put in the point 1. There's that blue dot there, that's the point I'm looking at. And now I'm going to make a polynomial. Bear with me. Okay. So the red line here, I should really make the green one. Let's just make it a dotted line so that I can tell it from the red line. So this red line is e to the power of x, and this green line is the Maclaurin polynomial. The Maclaurin polynomial matches your function at the point where x is 0. And so this is what I would have gotten if I had just put in 1 plus x. And then if I had done, oh no, sorry. X squared, that's the next Maclaurin polynomial, 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 that's the next Maclaurin polynomial. And if I just zoom out, you can see what's going on here. Change the degree, it gets more and more accurate for at least the positive numbers as the number increases. So what I'm interested in is zooming in on this point here. I'm going to make this where'd it go? All right, there's the point there. Zooming in on this point. So at the moment, the distance between the green function and the red line at this point is about 1.7. That's the distance so far. If I go to the next polynomial, now the distance is about, that's 2.5 there and 2.7, it's about 0.2. At 3, now the distance goes from 2.6, that's 2.67, I'm up to 2.8, so we've got 1, 2, 3, 4, 5, 0.5, 0.05, I think, ish, and now the distance is even closer. And so what I would like to know is what does the n have to be for this distance to be within 0.000005? That's what I want to know. So let's see. So there's 718,183, 718,182, so that difference is 0.0001. So let's see, how far do we have to get within this? Okay, we're within 0.001 now. And now we're within, there's 182, 183. I'm losing the accuracy. It's not telling me the things I want to know. Just give me one moment, see if I can draw something. So this zone here between these two black lines, this line is at E plus 0.000005. This black line is at E minus 0.00005. And I'm going to need to make my, there we go, we're in it. When n equals 8, here we are. It is now within 0.00005 of the correct answer. Cool. So let's just actually ask, what is P of 1? And what is E? So E is 2.718281, and this is 2.718278. So within 0.00003 of the answer. That's how far apart they are. And we had to get it to n equals 8 to get it within that closeness. So if I zoom all the way out again, there we go. You can't even tell from the big picture that they're all different at that point. But we've zoomed in all the way to get to that, how to say that to be within the distance we want, we have to get to the 8th Taylor polynomial, the degree 8 one. Because the degree 7 one back here wasn't close enough. It was much further away than 0.000005. So all of that's fine, and you don't want to have to do that process to make it work, but there is a formula which gives you an estimate of what this error might be. And that's called Taylor's theorem. So Taylor's theorem says I'll put a link to the Desmos on the website as well, the one that I just made, so that you can see it. Just try and remind myself to do that when I scan the pages. Put it on my hand as well. Desmos link. Okay, that'll remind me. Okay, so there's a theorem, it's called Taylor's theorem. And Taylor's theorem says, and I just want to copy it exactly from the notes. Taylor's theorem says that as long as your function has, you can actually calculate all the derivatives involved. So consider the Taylor polynomial Pnx for f of x at a of degree n, as we're going to think about that polynomial, okay? Sometimes they don't call, say, of degree n, sometimes they say the nth Taylor polynomial. That's the other one as well, so just bear with that in mind. Then, so first we're going to say what the error is. Then f of x will be equal to the polynomial and a bit. So in the graph I drew earlier, it was in red in the Desmos diagram, but I don't have red, so I'm going to do it in pink. And then the Taylor polynomial was like something like that, or whatever. It might have been below. That distance here, so to get to here, I have to go up to the Taylor polynomial and then down to the function. And so this is Pn of x, and this is Rn of x. And so in this case, the Rn is negative. But if my function was below, the Rn would be positive. My Taylor polynomial was below the function, the Rn would be positive. So people call this the error or the remainder. It's called the remainder because it's what remains when you remove the Taylor polynomial. And so it is literally the distance between the Taylor polynomial. So it's saying if you've already calculated the Taylor polynomial, how far do you have to go to get to the real function value? Okay. All right. And then that's not even Taylor's theorem yet. I'm just setting it up. Taylor's theorem says that whatever the actual answer is for the function and the Taylor polynomial, even if you don't know what either of those things is, you can estimate what this error is by doing this thing. So we're not going to have a then, I'm just going to say right. And then Rnx is a formula that will tell you what the remainder is. Without actually calculating either of P or F, it'll tell you what the remainder is. And the remainder is this. It will be the next derivative, the n plus 1th derivative of the function over n plus 1 factorial, x minus a to the n plus 1. So this looks extremely like the next term of the Taylor series, of the Taylor polynomial. But it's not quite the same, because instead of an a in this spot here, there is... What's going on? I didn't try to minimize Zoom. Zoom just did a weird thing. Okay, for some z between a and x. So what it's saying is, so this is Taylor's theorem. Some people call it Taylor and Lagrange's theorem. And it doesn't tell you exactly what the remainder is. It says that if you could, it says that it's possible to find the remainder if you could pick the correct value of z. And that value of z is different for every x. It's different for different x. That's really important. Okay. So it doesn't tell you actually what the remainder actually is. It just says that there is a number z that will get you the right answer, but it doesn't tell you what the correct number z is. It just says that there will be a z that's somewhere between the a and the x that we're thinking of. So for our function, there will be a z somewhere, because it's a Maclaurin series and the centre is 0, there will be a z somewhere between 0 and 1 that gives us the correct answer for this function. But we don't know which one it is, unfortunately. Okay, cool, excellent. And so what you have to do is you have to say, well, I don't know which z is the right z, so I will try all the different values of z and pick and say, well, these are all the possibilities for what the remainder could possibly be. This is the worst one. It can't be any worse than that. So what you have to do try all the possible z's and pick the worst one, then say, well, the absolute value of the error is less than or equal to something. That's how you're going to do it. Because the worst one is the one where it's furthest away. So I don't really care if it's positive or negative, I just want it to be as close as possible. Yeah. So that's how you normally do it. So I think we have enough information to actually do this problem now. But I just wanted to talk about all the details of the things so that it was all there. So I think we're just going to return to the problem. Okay, so I'm going to return to the problem. I'm going to let f of x be equal to e to the power of x, and Pnx is the Maclaurin polynomial for e to the power of x, which means that the centre is 0. And we know what that looks like. And Rnx is the remainder. Okay. Which means it's f of x minus p of n of x. That's what it is. But we are imagining that we don't know how to calculate e to the power of x, other than by using a Taylor polynomial. So I'm not going to calculate the exact remainder. I'm just going to leave it like that. And Taylor's theorem says that the error, the remainder for the degree n Taylor polynomial at x is f n plus 1 x on n plus 1 factorial times x minus 0 to the power of n plus 1. Because the centre is 0 because it's a Maclaurin polynomial. No, it's not an x, sorry, damn it. That'll be a z for some z. Z between 0 and the x I'm thinking of. That is what Taylor's theorem says. And so we would like the error, whether positive or negative, to be less than 0.000005. That's what we've been asked for. So we want the error when x is 1, because we want f of 1, which is e to the 1, which is e. That's what we want. So we want the error when x is 1, which is f n plus 1 of z 1 to the n plus 1 over n plus 1 factorial. For some z between 0 and 1. So we are now at a stage where it is possible for us to try and figure out what's going on. So I need to imagine, what could this be for all the possible values of z? That's my question I need to answer. And for that, I'm going to need to know what the n plus 1th derivative of f is. Now, I can't just use the next term in the Maclaurin polynomial, because that was calculated by putting 0 into the formula. So I'm going to have to actually just know what this derivative is. So f of x is e to the power of x. The first derivative is also e to the power of x. The second derivative is also e to the power of x. That's going to happen forever. ... The n plus 1th derivative is e to the power of x. It'll always be e to the power of x. That's the convenient thing about e to the power of x. And so therefore, Rn of 1 will be e to the power of z times 1 to the n plus 1 over n plus 1 factorial, which is e to the power of z over n plus 1 factorial. So I would like to know, for some between 0 and 1. Okay, well, this is the problem. if I imagine all the possible things that could come out of this when z is the numbers between 0 and 1, I'm going to have to know what the answer is for e. So it's a bit paradoxical. To figure out the error for e, I need to know what e is, which is, damn, okay. But I can look, the biggest possible answer that this could possibly give is e to the power of 1. So e to the power of z is between e to the power of 0 and e to the power of 1, because z is between 0 and 1. I'm just going to pop that in. Z is between 0 and 1. So that. Now, when you do a function on all three parts of an inequality, it doesn't always stay with the arrows pointing the same way, but it does for e because it's an increasing function. So that's okay. Okay, so I know that the error is definitely going to be bigger than 1 on n plus 1 factorial, but I want it to be small. So I know that, I'm just going to pick a number like 3, if that's okay. E is definitely less than 3. It's 2.71818. So I'm just going to leave it at that. Because all I need to do is pick a number that's definitely big and small enough, so I'm just going to keep it at that. And so the remainder for 1 is less than or equal to 3 on n plus 1 factorial. So if I wanted to be more accurate, I could pick 2.8. If I wanted to be even more accurate, I could pick 2.8182. Like I could just round off to the nearest whatever and just make sure I'm always rounding up to make sure it's less than or equal to. But I'm just going to pick 3 because I can't be bothered doing more decimal things than that. And so now I want the error to be less than 0.000005. And so if I arrange for this to be less than 0.000005, then the error will be as well. Okay. So I've been talking through this very slowly. If you were in an exam, you'd be able to do this a lot quicker because you wouldn't have to be explaining it aloud. Okay, so I need to solve this equation to figure out what the smallest n that works is. So first I'm going to move the n plus 1 factorial away from the bottom by multiplying both parts by that number and divide both parts by this. And so I'm going to get 3 divided by 0.000005 is less than n plus 1 factorial. I'm going to do two things simultaneously. I'm going to switch the n plus 1 factorial around to this side, and I'm going to figure out what 3 divided by this is. So 1, 2, 3, 4. I think it's going to be 60,000, but I could be wrong. Oh, it's close. It's off by 10. 1, 2, 3, 2, 3, 4, 5. I was close. Off by 10. I think that was pretty good though. If I'd written this in scientific notation, it might have been easier for me to do. Okay, and so now the easiest way is probably to just try different values of n until I get the first one that works, because there isn't an inverse function for factorial in your calculator anyway. I do know that n plus 1 factorial is more than, is less than, no, it's not going to work either. No, you're just going to have to try them. I know that n can't be 4 because that's only, the last factorial I know off the top of my head is 5 factorial, which is 120. And so n's got to be more than 4, so I'll start there. So I'll start at 5. So 6 factorial is 720, which is not big enough. 7 factorial is 5040, which is not big enough. 8 factorial is 4320, which is not big enough. 9 factorial is 362,880, which is not quite big enough. The next one will be big enough. So that's going to be greater than 600,000. And so therefore I'm going to choose n equals 9. So n equals 9. So P9 of x can estimate e to the 1 to within 0.000005. Now in our Desmos, we actually got it one step earlier than that. We got it at 8, which was the point that it started, but this is only an approximation. And so we had to go to 9 to be absolutely certain based on this argument. Yeah. But just to be clear, if I had done the 2.8, and if I'd done 2.9, yeah. Anyway, there you go. It is a long process. Yep. Yeah. But yeah, this is the only way to be sure, is to try them all. So for 5 factorial is the last one that I know the answer to, and so after that but I don't have to ask the calculator what a 6 factorial is, because I know what 5 factorial is. It's 120, and I can just keep multiply by 6, and then multiply by 7, then multiply by 8, and multiply by 9. But until I got to 10, that was the first one where it worked. But I was really close at 9. So it's probably, because this is only an approximation, this R is an approximation to begin with. Technically it can happen earlier than that, but we don't know for sure. So this is what they would have said. So the smallest value of n that we're sure of is 9. Okay. Pardon me. Okay, I just paused the recording for a bit to talk about what we're going to talk about next, and we're going to do a thing that involves eigenvalues, and this is my made-up problem. In an island nation, there is a large city, and the rest of the country is country. Each year, 20% of the population in the country move to the city, and 5% of the population in the city move to the country. Okay, so this is my story. So it seems to me that in general, people would drift to the one moment. It seems to me in general, people would drift, like we would end up with everybody living in the city probably, on average, but we'll see what happens, okay? So this is my imagining here. Here's the city. Here's the country. And 5% of these people move to the country, and 20% of these people move to the city. And then there'd be 95% stay in the city, and 80% of the country people would stay in the country. And so what we're going to do is we're going to represent these changes with a matrix. I'm just going to call them X and Y, if you don't mind, because they both start with C. I can't call them C because there's already two of them. So that X, N, be the number of people in the city. Well, we don't really know how many people there are, so maybe I should make it be the percentage of people in the entire country that are living in the city at the moment. Let's do that. I'll do a proportion, so it's a decimal rather than a percentage, right? And Yn in the country. Right, so what I know is that if I know that just both at time in year N since the start, like since we started watching. Okay. So what I know for sure is that if I took 5% of the people living in the city and added them to who was in the country, but also simultaneously took 80% of the people who were in the country and put them in the city, then I'd end up with how many were in the country afterwards and how many were in the city. And so I should say countryside, whatever. But so just to be clear, I know this. I'm going to write down the equation. You don't always write this down, but I know that the number of people living in the city next time will be 95% of the people who were living in the city before and 20% of the people who were living in the country before. Because all of those people are the people who arrive in the city afterwards. 95% of the people who are already here arrive back in the city, 20% of the people here arrive in the city, and so now it's 95% of that plus 20% of that is what's here now. And I also have that Yn plus 1 is 80% of the people who were in the country and 5% of the people who were in the city is now what is in the country. And look, that can be done with a matrix. I'm just going to write at the top of the next page so it's easier to compare if someone's reading this on a PDF. So if I make a vector that's got x n plus 1, y n plus 1, then I can do this with matrix multiplication. Like that. Because I can go 0.95 times xn plus 0.2 times yn, that's what this line is, and 0.05 times xn plus 0.8 times yn, that's what this line is. Okay. So this thing here is usually called a transition matrix. I don't know if that's what they call it in your course, but that's what they call it. If you're looking up things online, it's usually called a transition matrix. I'm going to write that clearer. Okay. So I could give that matrix a name like the capital A, and it'd be easier for me to think about what's going on. And I could give this vector a name like bold X, like underline X if I wanted. And so it's traditional to normally call this underline X plus 1, N plus 1 is the matrix A times the original Xn. That's usually the way we do it in symbols. Okay. So what that means is now it's all matrix multiplication and vectors and stuff. And so if I wanted to get to xn plus 2, I would multiply xn by a twice. And so I could say that x0 is the starting vector of proportions, and ax1 is the proportions in year 1, and that would be ax0 would come out to x1. I'm just writing this backwards. And that's the proportions in year 1, and a times x1 would come out to x2. Now I'm just going to write it the other way around. So proportions in year 1 would be a times x0, and the proportions in year 2 would be a times x1, which would be a times x0, which would be a squared times x0, and so on forever, right? This is the proportions. Year 2, and x3 would be a times x2, that's a times a squared times x0, which is a cubed times x0, and they're the proportions in year 3, and so on forever, you know, dot, 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 xn will be a to the power of n times x0. And so powers of matrices becomes a thing. Yeah. Not that yeah, that's all fine. So that's really kind of cool that powers of matrices suddenly become something useful in this sort of situation. But they really do use matrices to do population dynamics. Not as simple as this. It's usually more areas and groups of different people. And they have to include people being born and people, you know, immigrating and people leaving the country. And you know, so there's lots of, it's more complicated than this normally. Okay, so if I want to do a high power of a matrix, the quickest way is usually to use eigenvalues. You can, I don't know if diagonalization is a thing in this course, was it? Yeah. You could diagonalize that matrix and that could help you to do this calculation, but there is another way of dealing with it as well. And if you wanted to diagonalize a matrix, you would have to find its eigenvectors anyway. And it would be very interesting to know that if you had just the right proportions in the city and the country, and then 20% of the country people move to the city and 5% of the city people move to the country, if you had just the right numbers, maybe that would turn out that you would end up with the same number in both places afterwards as you had before. If the country was the right size, the number of people in the city was the right size compared to the number in the country, 5% of the city would be the same number of people as 20% of the country, and so it would all just be exactly the same as it was before. And so it is technically possible for how many people living in each position to be the same as it was before. And that would be a situation, so let's just imagine if you had like a really big city and not very many people in the country, and 5% of this and 20% of this. Imagine what if 5% of the city was the same as 20% of the country, then the proportions wouldn't change. That's what we're imagining. And in that imagination, if the proportions didn't change, you would get x naught and you times it by a and it would still be x naught. It'd still be the same answer as it was before. Let's just think about that. If you have a matrix times a vector and what you end up with is a multiple of the original vector, then this is an eigenvector. This is the same as ax naught is 1 times x naught. It's an eigenvector for eigenvalue 1. So one of the reasons eigenvalues exist is because of situations like this, why we're interested in them. We're really very interested in the vectors that come out to be 1 times the original vector. But it is possible to have a 2 in that spot, not in this story, but in other stories, it's possible to have other numbers in this spot. And so that's what an eigenvector is. It's saying it's a vector that when I do whatever process the matrix does, only changes by multiplying by a number. And most vectors won't do that. They'll change in other unpredictable ways. But no, actually they are predictable. It's maths, you can predict things. So they'll change in other ways, but some of them will do this. And so that's what an eigenvector is. So we're going to have to know how to find eigenvectors if we wanted to know. Right, so let's just step back a bit. If the population kept moving, but it did settle down eventually to be almost the same every time, we'd be drifting towards this eigenvector, the one that goes with 1. That's the idea behind it. It may not settle down to that, but I reckon it might. So here we go. We're going to need to know how to find eigenvectors. So the definition is this. So just a little aside. So you've got a square matrix A. You have to start with a square matrix, which means it's n by n. So if lambda is a number, so given a number lambda, it's traditional to call it lambda, that's what they called it in this course, yeah? Okay. Given a number lambda, a non-zero vector x such that ax is equal to lambda x is called an eigen. Oh crap, sorry, just a second. I really have trouble defining these in ways that are useful. Sorry, I'm going to just try that again. Okay. If the number lambda has a non-zero vector x such that ax equals lambda x, then lambda is called an eigenvalue of A. That's what it's called. And if a non-zero vector x has a number lambda such that ax equals lambda x, then x is an eigenvector of A. They're the same definition really, but one is about the number and the other one's about the vector. So if you've got a random number and you want to know if it's an eigenvalue, then you need to find an x so that ax equals lambda x. And if you've got a random vector and you want to know if it's an eigenvector, then you need to calculate ax and see if it comes out to number times x. All right. So it's easier to tell if a vector is an eigenvector than it is to tell if a number is an eigenvalue. Because to tell, so I should actually just say that. This is the definition. So, to tell if x is an eigenvector of A, do ax and see if it is a multiple of x, like a scalar multiple of x. So that's the definition there. And what the definition says is this is how to tell if a vector is an eigenvector of A. Multiply it by the matrix A and see what happens. And if it looks like it's a multiple of the original vector, great, it's an eigenvector. And the thing that that multiplies it is the eigenvalue that goes with it. To tell if a number is an eigenvalue, that's harder, because you would have to find a vector that does this, and that's much more difficult. So here's how to tell. So just some ideas. If AX is equal to lambda x, for x not being 0, but the lambda is allowed to be 0, by the way, then this is a tricky equation, because this side I've got a matrix times a vector, and on this side I've got a number times a vector. So it would be a lot easier if they were both matrices. So I'm going to do this. That makes it easier. Chuck an identity matrix in. Now, can I just check something? Does your lecturer prefer to do A minus lambda I, or do they prefer to do lambda I minus A? Or do they do both? They both are fine. It's tradition to do it this way round, to say that I'm going to subtract AX from both parts and leave behind a 0 vector. Sorry? What's that? Yeah, cool. You do that? Yeah, cool. So I'm just going to say I could have done this, like AX minus lambda IX equals 0. So A minus lambda IX equals 0. It doesn't really matter. You can do whichever one you like. So you'll get the same answer. There's one situation in which you'll get a different answer. It depends on what you're looking for. So, but if you're looking for eigenvalues, so this is just some ideas. You don't have to do this every time. If you've got a good enough memory, you can go straight to here. And so look at this. Now it's this. I'm going to stick with my lambda I minus A. If this matrix, whatever it was, if I chose a number of lambda and I figured out what this matrix was, if that matrix was invertible, then the only answer for x would be 0. And so if I want this to work when x is not 0, that matrix has to not be invertible, which means its determinant has to be 0. So since we have non-zero solutions for x, we need the determinant of this matrix to be 0. And now I have neatly gotten rid of x, and so I can just think about the lambdas. So to decide if lambda is an eigenvalue, I can do lambda I minus A and find the determinant. If it comes out to 0, lambda was an eigenvalue. If it doesn't come out to 0, lambda wasn't an eigenvalue. Yay. And we forgot to put the recording back on, didn't we? No, we didn't. Okay, it's all good. I remembered. Okay, so you don't have to show all this working every time. It's okay to go straight to here. Yeah. But if I actually did want to find the x's that went with the lambda that I'm thinking of, I would have to solve this equation here, like this equation here. I have a question. Was the phrase characteristic polynomial mentioned in this course? If you're not sure, okay. So this determinant will come out to be a formula involving lambdas, and it will be a polynomial. It's called the characteristic polynomial. So this thing here, this formula, now they might not have mentioned it in this course, but I just wanted to say that that's what it's called in case you wanted to Google it. And the only situation where you have to do it as lambda I minus A is to get the characteristic polynomial, because it's tradition for the characteristic polynomial to start with a plus. And if you do it as a minus lambda I, it'll start with a minus. So that's it. But other than that, it makes no difference whatsoever. If you're looking for eigenvalues, you can do either of lambda I minus a or a minus lambda I. If you're trying to look for eigenvectors, you can do either of them. It doesn't matter. Because it's equal to 0 anyway, and so it doesn't really matter. Multiplying it by -1 is not going to make a difference. That's why. Okay, so that's what eigenvectors and eigenvalues are, and that's how to find them. So if you didn't have any information about your matrix, so just wait. So to check if a vector, that number is an eigenvalue, find the determinant of lambda I minus a. And if it's 0, then it's an eigenvalue. And if the determinant of lambda I minus a is not 0, then lambda is not an eigenvalue. That's just a thing. It's not very common to do that, but I just wanted to point it out. So you could imagine, right? You could imagine an exam question that said, suppose for the matrix A, det of lambda I minus a is this formula. And then they said, is the number 3 an eigenvalue? And you can sub it in, and it wouldn't, and if it comes out to 0, it is, and if it doesn't come out to 0, it's not. Ta-da. You don't even have to tell you the matrix to be able to decide. All right, but the upshot of it is, if you have a random matrix and you want to find its eigenvalues and eigenvectors, so given A, to find the eigen and eigenvectors, step 1 is to this is how I would normally do it. I would write down lambda I minus a, or a minus lambda I, it doesn't really matter. 2, I would find the determinant of lambda I minus a. I would solve the equation made by whatever the answer is for determinant of lambda I minus a equals 0, and that will give you your eigenvalues. And then step 4 is actually one step for each of these numbers. For each eigenvalue, solve lambda I minus a x equals 0, which would mean that you'd get the matrix lambda I minus a, and you'd put zeros here, and you'd row reduce and put in free variables and stuff. You do row operations and stuff in this course too? Yeah, good. This course has got a whole lot of random things that other courses also have in them, so I just need to check where the line is. It's only existed in this form for about 2 years, so I'm still not 100% used to everything that's in the course yet. Like, I know all of the things that are in the course, I just can't remember what's in this one and what's not. Okay, so that's how to find eigenvalues and eigenvectors. There was another word that goes with this, which is called eigenspace. That's not really useful in the particular context we're working in, but it's worth pointing out. But I just want to, one more definition. given a number lambda, the vectors x such that ax is lambda x, like all of those vectors, all the vectors x such that ax equals lambda x together are called the eigenspace for lambda. And I think your lecturer denoted it like this, with a blackboard bold E. So just to say that there's lots of ways of figuring this out, but the main way of figuring it out is that, like, so just for maths notation purposes, E lambda is the set of x's such that ax equals lambda x. That's the definition in notation. So this is exactly the same statement as this, but in notation. But you could just as easily have the set of x's such that lambda I minus a times x equals 0. Same thing. And this is the one that's easiest to solve. So I've been very careful here. I didn't say that lambda was an eigenvalue. Technically, you can pick any number and find its eigenspace, but most numbers, the eigenspace has only got the 0 vector in it. So if I pick a number lambda that isn't an eigenvalue and I attempt to solve this equation, the only x that will work is the 0 vector. And so if you could imagine running through all different numbers and finding all these eigenspaces, and you would end up with, oh no, that one's got two vectors, like that one's got vectors, that one's got non-zero vectors, that one's got non-zero vectors, and whichever ones end up with non-zero vectors, they are the eigenvalues. Now that is not how you would go about solving this, because that would be too hard and lots of work, but just pointing it out. Especially because the eigenvalues don't have to be whole numbers. Yeah, they often are. If your matrix is made of whole numbers, your eigenvalues are often whole numbers as well, but that's rare. Okay. So just to point out, an eigenvalue is just a number. An eigenvector is a single vector. But if you look at all the eigenvectors together all at once that go with the same eigenvalue, that's an eigenspace. All right, we're ready now. So back to the problem. So my A was, I believe, 0.95, 0.2, 0.05, 0.8. And I'm going to find the eigenvectors and eigenvalues of A. Okay. So lambda I minus A is this. And I'm going to need to do the determinant of that. And so for a 2 by 2 matrix, the determinant is these two multiplied minus these two multiplied. So okay, lambda squared minus 0.95 lambda minus 0.8 lambda plus whatever 0.95 times 0.8 is. And that's what calculators are for. .76 minus 0.05 times 0.2, 0.0001. So I've got lambda squared minus 1.75 lambda plus 0.75. Okay. And I need to solve this being 0. I need that to be 0 in order to find the eigenvalues. And that's a quadratic equation, so I could use the quadratic formula if I wanted, or I could attempt to factorize this. They're my choices. So if I was going to factorize it, I would need two numbers that add to give 1.75, well, technically add to give minus 1.75, that also multiply to give 0.75. Oh, well, 1 and 0.75 will do it. Because 1 plus 0.75 is 1.75, and 1 times 0.75 is 0.75. So yes. Awesome. If my numbers were a little more random, I wouldn't be able to do that. But I will say something to you. The columns of this matrix each add up to 1. These two add up to 1. These two add up to 1. If that happens, the number 1 is guaranteed to be an eigenvalue. And so it was a good guess to see if 1 plus this came out to 1 times this. Like, yeah. And so my lambda is 1 or 0.75. They are the eigenvalues. Okay. So I'm just going to say, technically, to solve the problem I'm trying to solve, I don't actually need the eigenvectors for this problem. But I just want to do them just so that I've done it. So the eigenvectors, my abbreviation for eigenvectors is just E vectors. So eigenvectors for eigenvalue 1, I'm going to have to solve 1 lambda minus a x equals 0. And that's putting a 1 in for lambda in this matrix here. So I'm going to go back to this matrix and go 1 minus 0.95. So 1 lambda minus a is this. And so I've got 0.05 minus 0.2 minus 0.05, 0.2. That's what I'm solving, that thing. So this 0, 0 is that 0 there. That's this 0, 0 here. Okay. And oh, look, the bottom row is minus the top row, so I can neatly get rid of that. And I could probably multiply everything by 100 to get something a lot neater. So technically, these are the row operations I've done. Row 2 is row 2 minus plus row 1. That'll make us zeros in the bottom row. Row 1 is 100 times row 1. That'll do. And possibly I could divide by 5 as well. No, I don't like it. That's too many at once. I'm going to make a mistake if I do too many things all at once. We're at this stage, and then row 1 is a fifth of row 1. Like that. Cool. And so the goal here is to figure out what x and y are that go with this, because this is all actually, there's an x and a y here. There's a pivot column there, and there's no pivot column here, so this one's free. And so y, I'm going to let y be t, and then the x will be plus 4t, and so I've got that xy is 4t, which is t times 4, 1. So there's my eigenvector. These are all the eigenvectors that go with this eigenvalue. If I want all the solutions to lambda I minus a x equals 0, then I'll also include the 0 vector. So 0 vector is part of the eigenspace, but it's not an eigenvector, confusingly. Okay. So just to be absolutely clear that the answer is the eigenvectors for lambda equals 1 are t for 1 for t not being 0. But the eigenspace is t for 1 for t being anything including 0. Yeah. Okay, let's find the eigenvectors for lambda equals 0.75. So this time I'm going to have 0.75i minus a. Where's my lambda I minus a? Here it is. So that's that matrix. And so we're going to solve this. So 0.5 minus 0.75 is minus 0.2. And then 0.75 minus 0.8 is minus 0.05. Oh, look at that, it's gorgeous. The top row is a multiple of the bottom row. They're both the same number in both positions. And so if I divide this one by 0.2 and this one by 0.05, I'll know that they're both ones. So I'm going to do row 1 is minus 1 over 0.2 times row 1. And then once that's a couple of ones, I can do row 2 is row 2 plus 0.05 times the new row 1. And so that's going to get me 1, 1, 0, 0, 0, 0. You don't have to, when you're doing this process, you don't usually have to say the row operations unless someone asks you to. But I just put them in to be absolutely clear what was going on. And so now I've got, yay, it's so good. So now pivot column there, I'm going to make this one free. So then x is, I put that over there, it'll be a minus 1, so it'll be minus t. And so x, y, what's that? Oh, you don't have to use different unknowns, you could have just called it y. Is that what you're asking? Oh, the other one had a t? Yeah, I don't have to use it, I can still use a t for this one. That's okay, because I'm saying that this choice for all possible t's is this eigenspace, and that choice for all possible t's over there is that eigenspace, so that when people read it, they know that both of them cover all the possible values, so it doesn't really matter. So I've got a minus t for x and a plus t for y, which is t times minus 1, 1. And yes, you could use a different letter here if you wanted, but nobody cares. So the eigenvectors for eigenvalue lambda equals 0.75 are t of minus 1, 1 for t not equal to 0. Okay. I just want to check if I've done it right, okay, just to be absolutely sure. So let me just check them to see if they really are eigenvectors. So just check. So the matrix A, going back to my original matrix A, which was 0.95, 0.2, 0.05, 0.8. When I multiply that by, was it 4, 1? Yep. I get 4 lots of 0.95 plus 0.2. 4 times 0.95 plus 0.2 is indeed 4. Yep. And I'll have 4 times 0.05 plus 0.8. Well, that would be 0.2 plus 0.8, so that really is 1. So yes, it does come out to 1 times the original, and so it really is an eigenvector. Whereas with the other one, oh yeah, I got minus this plus this, which would be minus, so minus 0.95 plus 0.2, and that really is minus 0.75, and I've got minus 0.05 plus 0.8, and that really is plus 0.75, and that really is 0.75 times the original vector. Yes, okay, it works. It's not the worst plan to do that if you've got time. All right. So cool. So if I had been very lucky, I could have guessed that eigenvector there. I was going, oh, what if I did the first one minus the second one? Yeah, that'll work. And that would have shortcutted the process a little. Okay, so those are the eigenvalues and those are the eigenvectors. So here's the thing. So two possible eigenvectors for different eigenvalues. So if lambda equals 1, I can choose 4, 1. And if lambda equals 0.75, I can choose minus 1, 1. So I'm just picking one eigenvector for each eigenvalue. Those two vectors are linearly independent. That's a word we've got in this thing, yeah? So being linearly independent, and there being two of them, that means that every vector with two coordinates can be written as a combination of those two. And just to look, like this one plus 4 of that one will give me 0, 5, which I can divide by 5 to get 0, 1. And if I can get 0, 1, then I can use this one and 0, 1 to make 1, 0. And so I can make 0, 1 and 1, 0, and if I can make those, I can make anything. So that's the idea. So these, is the word basis in your course? No, it is, yeah. These are a basis for the whole of R2. Which means that no matter which vector I have, I can write it as a combination of these two. So therefore, for any vector x naught that I could have started with to describe how many people were in the city and the country, x naught would be something times 4, 1 plus something times minus 1, 1. For some a and b being real numbers. I don't know what they are, but they do exist. I choose not to find them because I don't know what x naught is anyway. And, well, now if I multiply x naught by a, well, a times x naught would be a times a of 4, 1 plus b of minus 1, 1. Oh, can I keep these vectors names? I shall call them u and v. Because now I don't have to keep writing all sorts of things, u and v, like that. And that's the same as a times au plus a times bv, and the numbers can come out, so I'll get this. But u was an eigenvector, and its eigenvalue was 1. And so au is the same as just, capital AU is the same as u. And v was an eigenvector too, and its eigenvalue was 0.75, and so this is what I'm going to get. And if I had a squared times x naught, that would be a times the thing I just made. And the same thing's going to happen. I'm going to get a times au plus b times 0.75 times av, and that's going to be au again, and I'm going to get b times 0.75 times another 0.75. Right, just absolutely clear. So I'm going to get au plus b times 0.75 squared times v. And so this would continue forever, right? A to the power of n x naught would come out to au plus b 0.75 to the n v. Cool. All right, here we go. This is xn. So 0.75 is a number less than 1, so if you raise it to a very high power, it will get closer and closer to 0. So as n gets larger, 0.75 to the n goes to 0, and so therefore xn will go to au plus b times 0v, which is just au. Cool. So that's great. Lovely. So if you had x naught and you could figure out what multiple of the vector u it was, like, there'd be another bit with the other stuff, then you would know what xn is going towards. But there's one more piece of information which is even cooler. But just wait. This is a times 4, 1, right? Which is 4a. And that means that regardless of what a is, the number in the x position is 4 times the number in the y position. So what that means is, if this is xn, yn, then that means that xn is 4 times yn. Yeah. So there's going to be 4 times as many people in the city as there are in the country. Eventually. Yeah. And so that means, the total population, yeah, the total, so eventually 4 times as many people in the city as in the country. So that means that it'll be like 20% in the country and 80% in the city, because they have to add up to 100%. So we know that as percentages, because that's what the x's and y's were, we know that xn plus yn is 100%, and we know that xn is 4yn, and so 4yn plus yn is 1, and so 5yn is 1, and so y is a fifth, which is 20%. And so therefore the xn must be 80%. Yeah. Cool. So you don't have to show all that working. You can just say, well, xn and yn have to add up to 1, and therefore like that. So eventually there will be 20% in the country and 80% in the city, regardless of how many there were to begin with, unless there was 0 in one of them. No, that would still work, because the 20% would go to the city and then there'd be 20% in the city. Not that you ever have empty cities. In an island nation, there are, in big countries with several 100 million people in them, there are empty cities. So, not least because there's been a nuclear holocaust in one of them. So, not holocaust, but Chernobyl doesn't have any people living in it because it had a nuclear disaster in the 80s. Or was it the 90s? Anyway, it's empty. And actually in China, there's empty cities just because they're waiting for people to put in them. So like that, they don't do that in other countries. That's a Chinese thing. So it's cool. Empty city, just little ones. You say, well, we're just going to build a whole lot of places for people to live, so that when we build the factory there, they'll have somewhere to live. So, yeah. But you can only do that in countries that are very large, with lots of people. I think that happens in India as well. So, yeah. Anyway, that's irrelevant. We can have 20% in the country and 80% in the city in this pretend story. And I just want to point one last thing out. This 4, 1, if I'd added them up and gotten 5 and divided by 5, that would have given me this 0.8 and 0.2. Because we're going to drift towards the eigenvector in this eigenspace, because that's what we get. We end up with A times U. And since it has to be a vector that adds up to where the numbers represent percentages, I can just divide them by the total and that will give me the percentages. But it doesn't always work out that way. So I will say some of these stories that aren't about percentages moving from one place to another and that are about like animals eating each other, sometimes you don't get one being an eigenvalue. And you end up with both the eigenvalues both being less than 1. And so you end up with this thing here ending up with A times something to the power of n plus B times something to the power of n, and both of those numbers go to 0. And so eventually the answer is just 0, 0, and all the animals die. And so there's a very famous story of people using matrices to argue for ecology, where there was a species of owl, and they managed to model the number of owls in different age groups using a matrix, and then showed that all the eigenvalues were less than 1, and therefore if they kept going the way they were, that all the owls would die. And so that convinced the government to put in protections for the habitat. Doesn't work for our country very much. They're still not looking after our koalas very well. So we'll get there. Yeah, cool. Thank you for listening.